Okay, before we start, are there any questions? Okay, so I would also like to see if if I could move the Tuesday class to say a Wednesday at 6:40. I'll post that on Slack so that people can respond to that. Okay, so we were discussing the adjoint representation. And I just sketched it. I didn't really give you the details. So what is the adjoint representation? So suppose you have a Lie group. And G tilde is the Lie algebra. So we can define an action of an element G of G on the Lie algebra by the following way. So we call this action the adjoint action, an action known as the adjoint action. And the way we define it is that the adjoint action of the group element G on a Lie algebra element, say T of A, is given by G TA G inverse. So it's conjugation. Okay, so this is how the adjoint action. Okay, so this is a definition. So note that now if we define say T tilde of A to be G TA G inverse, note that this thing depends on G, right? So we could have, we are not taking that into notation, but if you were serious, we would have written, we are serious, but if you wanted to be absolutely thorough, we would have to write TA, which depends on the element of G, right? But I'm just not going to bother with writing this. Okay. So if you define this, then we see that if I now compute the commutation relationship of, say, the tilde commutator, then it's just a one line of algebra to show that we get the same Lie algebra as the generator's T. Okay, so T tilde and the T's, they generate the same Lie algebra. They satisfy the same algebra. So this means that the T tilde, these guys are also elements of the Lie algebra, right? They are not elements of the group or anything. They are elements of the Lie algebra. Okay? So this motivates, yeah.
The difference in indices, is that significant between the two structure constants?
No, I just forgot. Yeah. It's exactly the same. You basically, derive this thing from this thing, right? If you just apply G inverse on both sides, you just get this, right?
Yeah, makes sense.
Okay. So this motivates the claim that the adjoint map is a representation of G. The adjoint map, it's actually, we use the capital A here because there's going to be another adjoint map, which will be the map on the level of the Lie algebra. So the adjoint map, which is a map from, say, the Lie algebra to itself, right? And this is some kind of a, we can think of it as a vector space or a module or something like that. So the adjoint map is the adjoint map is a representation of G. Acting on, G usually acts on some vector space, but in this case, the vector space that it acts on is G tilde. And this representation is known as the adjoint representation, okay? It's a very special representation that plays a very important role in the theory of representations. Okay, so let's formalize this a little bit and prove these statements. Now, since T tilde is an element of the Lie algebra, we can write T tilde of A, which is defined to be the adjoint of G acting on T of A. And this statement means that we should be able to express T tilde as linear combination of TAs. So let the coefficient of linear combinations of TAs, let's write that at CAB. Of course, it's a function of G, and B is a repeated index. That means that it is summed over. Okay. So we now want to find what these C's are. Now, let's take an infinitesimal element of the group. For an infinitesimal element, say small g of G, we can write G as 1 plus I theta C TC, right? So because C's are, C is a function of G, we can do a Taylor expansion. So C of AB, which are functions of G, then has a corresponding Taylor expansion. And the first term, of course, is going to be the identity. And then we're going to have minus I theta C, del of C AB divided by del of C plus dot, dot, dot. Okay. So we can write this as delta AB minus I theta C F ACB. Okay, so this is basically, these coefficients. It's taken for at the value of G equals to 1. Okay? So now, so we have C of A, B of G to be this thing. On the other hand, if I take the equation dg of TAG inverse for small values of the parameters, this is equal to T tilde of A, right? So on the left-hand side, we have 1 plus I theta C TC TA and 1 minus I theta C prime TC prime. I'm just expanding this guy and this guy on the left-hand side. On the right-hand side, I can write this as T of A minus I theta C F of A CB T of B. So the left-hand side is, we have until first order in theta. The right-hand side is second order, so we can ignore the second order term, and then we can write this as an equality. Then the left-hand side becomes TA plus I of theta C, commutator of TC and TA. And that is going to be T of A minus I theta C F of A C B T of B. Okay? Is that clear so far? We're just keeping until the linear order terms. So then we can, cross these out. And because these thetas are arbitrary, small but arbitrary, so we can drop those guys. And then we have, as a result, the commutator of TA and TC is F A C B T B. Okay? So this is very, very suggestive.